This is Module 11, Lesson 1. You guys, this is our next to last module. How exciting is that? I know that you are ready to be done, but I would like to encourage you to not give up, finish strong. You are so close to being done, so put your effort into it and make the most of this here at the end. I would like to encourage you as we start this next to last module to perhaps consider that your focus will need to be slightly different for the last two lessons. Unlike the rest of physics, we've had 9 heavily math-based modules, or what, 10? No, I can't count anymore. We've had 10 heavily math-based modules. These last two are not that at all. They are very heavy on the concepts, which means a lot of vocabulary words to memorize the definitions of, a lot of concepts to put in your head. The biggest thing that I could think of that that's going to mean to you is a difference in your quizzes and your tests. So what I mean by that? Well, the dogs don't like this idea apparently. What I mean by that is when you get ready to take your first checkpoint for Module 11, what you're going to have is very, very little time to complete the module because, I don't want to give you an opportunity to look things up. So be very, very prepared to take that quiz before you start it because there is going to be very, very little time to take it. If you're not prepared with the material, you're not going to have enough time to look it up. Granted, you still get your extra 2 chances after that, but it's going to be the same for those. Same thing goes for the test. So if you have questions, let me know. Otherwise, this is a good bit to just put in your head. All right, enough of my soapbox about what this is going to be like. Let's get to the lesson. So we're talking about magnets, and here's the deal with magnets. Magnets, I'm hoping you already know, can attract or repel things. You've probably played around with magnets before, the things that you stick to your refrigerator to hold stuff onto the front of it. Like you can, like sometimes at school we stick magnets to our whiteboards because they're magnetic, but there's a lot of other ways that you use magnets in everyday life. Like we have magnets in the fire doors at school. If you've ever noticed in the school building, when the fire alarm goes off, what happens is that there's certain doors that close themselves. And it's because they're magnetic. And when the fire alarm goes off, it releases the magnets and those doors close. So there may be even places in your life that you have magnets that you don't even know that it's there. Now, how is it that magnets are able to do this to each other? If you've ever played around with them before, you know that if you have one magnet here and one magnet here, and if you start moving this one towards it, sometimes like you can actually pull them together before they ever touch, or it might even end up like a game of chase. As you push magnet 1, magnet 2 might move. So the reason that these are able to interact with each other, either to pull themselves together or to push each other around without actually touching, is because they are surrounded by magnetic fields. Now we studied electric fields, and remember how we did like a positive charge, and we drew the field lines coming out of the positive charge. I'm not going to do all the arrows, but they came out of the positive. And if we drew a negative charge, they were going into the negative from all different directions. And, the magnet stuff is very, very much like the electric stuff. There are electric fields surrounding electric charges, and there are magnetic fields surrounding the magnets. Now, very similar to the charges, there is a difference in the density of the field lines. This is called magnetic flux. The closer that the field lines are together, the stronger your charge is going to be on the magnet, or the magnetic pole is going to be. With magnets, we don't have just a north or just a south. Magnets each have 2 different poles. They're going to have a north and a south pole together. So unlike our electric charges, you have to have one of each. Now let's look at magnetic fields. We had some rules for electric fields, so we also have some rules for magnetic fields. Magnetic fields are going to go from north to south. That means they're going to come out of the north and they are going to go into the south. So we could start with this one right here. This is called a bar magnet. So basically, you might get the idea from these over here that our field is going to go out of the north and into the south. And so I'll probably do that way too far away. So we're going to get the best drawings that Miss Houston could do with this, which may not be the greatest with my touchpad and this. They're going to exit from the north. They're going to head out in this direction away from it, which is exactly what's happening over here. As you can see, coming out of the north, and they are going into the south. That's on any magnet. It doesn't matter what shape it is. If we had like a little disc magnet sitting here and we knew that north was up top and south was on the bottom, same deal. They're going to come out of the north and into the south, around and around and around, just like this, okay? So what happens if we put them together? If we take two bar magnets and we put them with opposite poles together, like the north pole of one magnet to the south pole of the next, then what's going to happen is they are basically going to reinforce each other. We're going to see that it flows out of the north, and instead of going into its own south and wrapping back around, it's going over to the opposite south pole. I don't know what just happened to my pen, but there we go. It's going to go from here, and instead of wrapping around, no, it's going to go straight across. And what happens is you get a really strong field between the two magnets. Remember, we already said that the closer the field lines are together, that's called magnetic flux. The magnetic flux is going to be the greatest right in here where there's a big density, and right in here where they're closer together. And then it's going to be much weaker out here because they're much further apart all the way around in this area. It's going to be much weaker because they're so spread apart, and much more dense right in here. What if we put two bar magnets together with like poles? So when we have two like poles together, it works just like it did with positive and negative charges. They don't like each other. They are going to repel. So it's destined to come out of both of the norths. But instead of going across to the other side, they are going to push away from each other and never come together and reinforce each other because, well, they don't like each other. We still have a much greater density in this area. So it's going to be the strongest fields in here and weaker still further out. So here's some more of magnetic fields. I couldn't exactly find pictures that I wanted to of these. What if we lay them side by side instead of end to end? Well, what happens in this case is that these don't like each other, right? We have two norths together and two souths together. And what would normally want to happen is they would normally want to come out of here and swing around and down to the south, but we can't because this is in the way. So what's going to happen is we're still going to see our north exiting from both of these. They're going to come up and out in this direction. Hopefully that makes sense. But over here, they're going to be pushed away from each other. They're going to have no choice but to swing around to the other side of the magnet without being able to cross over very much on the other side. This is a horrible drawing on my part. They look like two giant kidneys. So they're going to swing into the south side after coming out of the north, but they're never going to do a whole lot of interacting in the middle. You might have just a couple of fields coming out and down and heading down towards the south pole, but they're never going to overlap and reinforce each other. Whereas take these two. Here, remember, they come out of the north and they want to go into the south, so what they're going to do is they're going to be able to just boop, go right over here, and they're going to reinforce each other very strongly. Same deal here. They're going to come out of the north and into the south. I'm ready to like muzzle a couple of doggies who must be barking at things outside. We're also still going to get these here. And you'd still get some fields going in on this side too, because we've got clear north-south ability to interact here. Okay, so let's talk about magnetic fields as vectors for just a minute. Remember with the electric fields, we said that electric fields were vectors. Well, so are magnetic fields. That's why we draw the arrowheads on them, because they have not only a magnitude or a size, but they also have a direction. And so one of the things that we could do as we look at this is we could look at a compass in the vicinity of a bar magnet, and we could see that the magnetic fields would go in the direction that a compass would point. So, you know, hopefully you've seen a compass before. Some people call it a compass, but I say compass. Basically, if you took a compass and you put it right here, then what you're going to see happen on the compass is you are going to see that the arrows are going to point in the direction that the fields are going. So if you put a compass right here, you would see that it points this direction. It's actually going to point to the north because those field lines are heading out of the north. And then what we said that would happen to the fields is that they would head, like out and around and down, right? Well, if you put the compass right here, you would actually see that it would point in this direction because it's the direction that the field is now going. And then as it's over here on the south side, it would point this way because they turn and they come back in. If you put the compass on this side, you would also see that it points down this direction because those field lines are coming out and around and down and back in. And so, interestingly enough, the compass is going to help you figure out the direction that things are going. Now, a little bit more about magnets, just to sum up some things. Remember, it's very much like electric charges. However, remember that electric charges could be single. You have a positive or a negative, whereas with magnets, you have them in pairs. Like you have to have a north and a south pole together. Interestingly enough, if you have a bar magnet, like one of the pictures we've been looking at, it's got a north and a south pole on it, and it gets broken. Let's say it drops and it falls on the floor, and I don't know if I can make this match up exactly, something like this, and it breaks into two pieces. This was our former north pole, and this was our former south pole. What you would see that would happen is you would have a new south pole and a new north pole form on these two little magnets. You still have both north and south pole. And if by chance this got broken again, let's just cut it right here like this and say we cut it right there on those lines, we're going to have a new south pole and a new north pole and a new south pole and a new north pole. Now you have 4 baby magnets instead of 2 little magnets. So, no matter how small you chunk these down into, they're still going to have both poles. Remember, above all, that you should already know this, that opposite poles are going to attract and like poles are going to repel. Now, a little bit about magnetism in the earth. And this is, some of it is information that you do need to know, and some of it's, kind of just for curiosity's sake. But, let's think about a compass again for just a minute. You know that if you carry a compass, it always points north. It shows you which direction that you are going. So, interestingly enough, Earth is just like a giant bar magnet, basically. Our geographic North Pole is actually the magnetic south. Now, it's not necessarily referred to that way. There's a lot of confusion here with this, but, basically I think there was an agreement to refer to the geographic north as the magnetic north, but technically, it's the magnetic south pole of the Earth because of just the orientation of our magnetic fields at this point in time. Earth's magnetic fields do some really cool stuff for us. Animals can migrate based on the magnetic fields of the Earth. That's how they know whether they're heading north or south because they can sense those fields. Our magnetosphere is basically like our big magnetic field protects us from solar winds. There's a lot of radiation that is given off by the sun, and if we did not have that blanket of protection, most living things would be killed by those solar winds. But instead, when those solar winds interact with our magnetosphere, we get the aurora borealis or the northern lights. You also have a southern version because it's a play of those two things together. It's a play of the solar wind with our magnetic fields leads to those kind of eerie colored green lights. Now, I didn't put anything in writing about this, but interestingly enough, Earth's magnetic fields have reversed multiple times over the centuries, and so you can actually see the reversal of the magnetic fields trapped in old samples of rocks. That's one of the ways that we know when and how often they've reversed. So this will not forever be the magnetic south pole. At some point, it will be the magnetic north. It's going to be a long time before that happens, though. Oops, there we go. So before we quit, what exactly makes a magnet? So what makes a magnet is basically some materials are just more likely to be magnetic. They're called ferromagnetic materials. It's iron, nickel, and cobalt. And what happens in these is that their unpaired electrons spin in such a way that makes them be aligned. And that's called domains. So when you have domains that go in every different direction possible, they're unaligned, you have a non-magnet. This is a non-magnetized piece of material. When they all spin in the same direction, though, and the domains align, you have a magnet. Now, you can sometimes create a permanent or a temporary magnet. Permanent magnets are things that are always magnetic. Like if you have your fridge magnets, those are permanent magnets. They are always magnetic. You don't have to do anything to make them magnetic. They just are. Their domains are permanently aligned. But you have some things that you can temporarily magnetize. An example might be if you've ever taken like a magnet and put like a paper clip on it. That's kind of a bad paper clip. And then you've used the paper clip that's attached to it to pick up another paper clip and maybe another paper clip. The idea that this paper clip is touching this one makes it a magnet, which makes this one a magnet. You're making temporary magnets out of these paper clips here because whenever you take them off of the magnet itself, the permanent magnet, they'll no longer be magnetic. You can also take a paper clip and rub it on the permanent magnet, and that will sometimes temporarily make it a magnet. Another example would be electromagnets. Things like the fire doors at school, like I was talking about, where they let go whenever the fire alarm goes off. Those are electromagnets. They are temporarily a magnet when electricity is running through them, but as soon as you cut the electricity off, nope, no longer a magnet. So now it's the end of the lesson. Now what? You do not have a practice sheet. I don't have a lot of things that I could have you do with this that's not just redundant. So you need to make sure that this stuff is in your brain before you take the quiz. And if you have any questions, you can let me know. Otherwise, it's up to you to listen to this and to memorize it as needed.